This is the nanoKenbak-1. It's a reproduction of the Kenbak-1 personal computer, which was created in 1971 by John Blankenbaker. The Kenbak-1 is widely considered to be the first commercially available personal computer. This modern reproduction is created by Chris Davis of Adwater Stir and uses the software by Mark Wilson. While the original device doesn't actually contain a microprocessor and instead was comprised entirely of TTL logic chips, this modern reproduction uses an Atmel 80MB328P microprocessor, seen on the right-hand side here. This chip is the same chip that's at the core of the Arduino. This device is powered by a rechargeable lithium-ion battery, as seen on the left here, and is recharged via a micro USB cable, which I'm going to plug in now to make sure we don't lose any programs once we start programming the device. I'm going to go ahead and stop this program now, pressing the stop button. The Nano Kenbak came with a brief instruction leaflet that describes the history of the Kenbak-1 and some of the extensions that are available for this particular device, which we won't be using today. It also makes reference to its rechargeable battery, which I've already mentioned. The original Kenbak-1, however, was aimed at the education market. Only approximately 50 of the machines were ever produced, and around 14 of the machines are known to exist today. Aimed at the education market, it came with comprehensive technical documentation, including a theory of operation manual, the programming reference manual that we see here, and a very extensive laboratory exercise book. The programming reference manual is very handy if you are already familiar with programming and would like to pick up programming on the device, and it contains important information such as the addressing modes of the device and very detailed information about how individual instructions work, their bit pattern layouts, and how they might affect the device and its memory. A particularly nice feature of the programming reference manual is that on the inside cover it has a photograph of the original Kenbak-1 device. Now, of course, you can see these online, but this is a very nice representation. The original device was significantly larger than the Nano device we're going to be using today, but they are essentially functionally identical. So let's go ahead and look at how we can use and program the device. So I've made a copy of the summary of coding instructions sheet, which we'll probably refer to a little bit later when we think about how the program works. But to start with, let's have a look at an example program from the lab exercise book. This particular program is a binary decimal test game and was presented early in the lab notebook. You can see it on page 4-3 of the book, and I will make links to all the documentation in the description below. Because this is a very early program in the book, the purpose of it is only really to help people understand binary and how to convert it to decimal, and so it's actually presented entirely in binary to make it, I suppose, easier for the beginner user to enter into a Kenbak device. Here, I've converted it to the much more common octal notation. So this is a worksheet that's available, and again, I'll link to copies of these, that allow you to write up programs and code them up by hand before entry into the device. We'll talk about the different representations of code and binary data as we start entering the program into the Kenbak. So let's take a closer look at the Kenbak itself. So here is our Kenbak device, and Nano Kenbak-1, and we can see it's got a series of buttons and LEDs on the front of the device, and we've already seen the start and stop button on the right hand side here that allows us to start the currently entered program and stop that program as well. On the left hand side you see a series of 8 buttons, and these are matched to 8 LEDs, and this is the user input and display output. At the moment the computer is in program execution mode, indicated by the LED immediately above the run section of the buttons here. But if we press any of the input buttons, it will switch to input mode and allow us to individually toggle those LED lamps. So let's go ahead here and press any of the input buttons, and you can see I can now easily toggle any of those LEDs on and off. If I'd like to clear them all at the same time, which is often a handy thing to do, there's a clear button here immediately below that input LED. We also have buttons to control the address, to display the current address and set to the current address, and read and store to memory. If we press the display button, we'll see the address location that the Kenbak's currently considering. and apparently that is address 0. We can read the contents of that location by pressing read, and we can see inside address 0, we currently have this particular bit pattern. If we press the display button again, we will have advanced to the next location as part of the read operation. So we should see a single LED illuminated here, and we do. So we're now in address memory location 1, and we can read what's in that location, and this is what's in address memory location 1. Again, this has advanced the counter, and so if we choose to display again, we'll see we're now in memory location 2, and this is a binary representation. We can also go ahead and use the set and store buttons to allow us to set the address and store data to memory. So we're going to need to do that to enter our program, and our program is represented here in the lock or location information and the data that's supposed to go into that location. So we can see we have a location of 0, 0, 0, but what does that really mean? Our device here has 8 LEDs because it is an 8-bit machine. Although the original Kenbak device processed that data serially, 1 bit at a time, it can process 8 bits as a chunk together. So we have 8 bits, and in the modern era we would call that a byte, and I'm sure we did back in the 1970s as well. However, there are other notations we can use to represent binary data to make it a more compact form. One of the more common available today is hexadecimal notation, and as we can see here, there is a representation of hexadecimal by grouping the 8-bit data into 2 chunks of 4 bits, and that's what we use for hexadecimal. And you can see that's represented by the 1, 2, 4, 8 group here, and a second group of 1, 2, 4, 8 here, and that would represent in hexadecimal notation. That was presented on the original Kenbak-1 device, and of course is recreated here. Another way of thinking about binary data is in what's called octal notation. Now, this was very common in the 1970s and early 1980s when John Blankenbaker was designing and building these devices. Now, octal notation splits the 8 bits into 3 groups instead. A first group here of 3 bits, 1, 2, and 4, a second group of 3 bits, 1, 2, and 4, and a final group of just 2 bits, 1 and 2. Now, this gives us 3 final digits in our representation for human viewing, and that's why we have 3 locations here. And any of these can be set to any value from 0 to 7 for these lower 2 cases here, and from 0 to 3 for this upper case here. And that works by simply saying that we have 1 here, and we can plus 2, which gives us 3, and plus 4, which gives us 7. As you can see here, because we only have a maximum of 2 binary digits, we can only plus 2 and 1 together for the maximum value of 3. Okay, so what we need to do here is we need to make sure that we are starting our data entry at address 0. And so I'm going to go ahead and do that by making sure I've cleared the input buffer. I've already done it here, but we can press the clear button to confirm. And then we can go ahead and we can choose to set the current address. You see the address light briefly flash there, and that indicates that we have indeed set the address to 0. We can actually also confirm that by pressing the display at any time, and that brings us back and shows us that we are currently displaying the address and it's currently 0. I'm going to switch back to input mode by pressing the clear button here, and I need to enter the data 0. In the Kenbak notation, we talk about a constant equaling 0 when we're doing that, and we're going to enter that 0 value, and we do that by storing that data in that address location we've already set by pressing the store here. So that stores the currently displayed or currently input mode values into the memory address that we've previously set. So store. Now this is being stored into location 0, and location 0 is a bit of a special location. As you can see here, it's pre-printed on the worksheets here, in that 000 represents the A register, where most of the calculations actually happen. The Kenbak has a few other registers, and we'll discuss those as we enter the data for those as well. The next location we will have already advanced to, so when I press the read or store buttons, we advance the counter, and I can confirm that by pressing the display button, and it says we're now at location 001. Okay. And in this location, we again want to put 0, so I'm going to clear the input register, and I'm going to store the data in 001. And again, that will advance the counter. I can confirm that if I choose to do so, but I don't have to by pressing this button here, the display button. And this confirms that we are now at the location 2. Okay, so 2 plus 0 gives us 2 in this location. There's zeros in both of these as well. Again, we want to enter a 0, so I'm going to press clear here and store. And now we're going to be in location 3. Location 3 is another special location called P, and P represents the program counter. This is the location that the computer is currently executing code from, or will do when we press the start button. So in this case, we want the P location to represent the start of the program. If we look down here, there is a label we've got called start, and that's at location 6. And that's why in the data, in the program counter, we start with the contents of 6. We set that by going 0, 0, 4 plus 2 for 6 in this location here, and we can store that as well. If I display here now, we should see that we're at location 4 because we've advanced past the program counter. And this is another case where we want to just enter 0, so a constant of 0. And it has a label check, but we'll get back to that later when we run the program. So I'm going to go ahead and clear that and store. In location 5, we want to enter 377, and so 3 is 2 plus 1 in this digit, 7 is 4 plus 2 plus 1 in this digit, and 7 is 4 plus 2 plus 1 in this digit. And so that's actually all of the LEDs illuminated, and we're going to go ahead and store that here. And this is actually referencing a label called input. And input is another special label, and that represents the input data location. So when a user is using the program or even using the device, data is temporarily stored in this location 377 for processing. Now I'm going to go ahead and enter the rest of the program here, and I'm going to fast forward through that part of the video for you, and we'll resume when we have completed program entry. Okay, so I've finished entering the program here, but I do think I made an error at one point during that. And it's very good always to go through and check the program entry to make sure the program in memory is what you expect it to be. At the very end of entering the program, we would have expected the memory address location to advance to the next location because every time we press read or store, the counter advances. So one way of checking if we're entering a sequential program like this is to go ahead and press the display button. And so we would expect to see 32 because that's the address after the last program line that I need to enter. As I mentioned, I think I made an error. So what I'm going to go ahead now and do is go through and check the contents of the memory. And so if I clear the input buffer and I set the address, this will move us back to memory address 0, which is at the beginning of our program here. We then want to read the memory. So we press the read button here, and this allows us to display the memory on the display. And if we press that, we'll see 0, which is actually what we expect in this case. If we press it again, we should see 0. And if we press it again, we should see 0. I can at any time choose to display the address. And so I can see the address after that read will have advanced. So if I display this now, I should see 3, and I do. And if I read the memory here, I should see 6, which I do. So that's all good. I'm going to go through and find the error, and then we'll resume and talk about how you might go ahead and correct that. Okay, here I am at memory address location 14, and I'm expecting to see 331, but I obviously didn't press this button correctly, or I accidentally toggled it incorrectly. And so I should see the contents 331 at this location, but instead I'm seeing 330. So we need to go ahead and correct this. If we press the display address button at this point, we'll see we're actually at memory location 15, because once I press the read button, it's advanced the counter. So if I press the display button here, we'll see I'm now at memory location 0, 1, and 5. So the first thing I'm going to need to do is I'm going to need to move back to address location 14 to correct the program. And so I'm going to go ahead here and clear this and set location 14, 0, 1, and 4, and set the address. And then I'm going to go ahead and clear the input buffer and make sure I correctly enter 3, 3, 1. I can then store this in the memory location. And if I display the address now, you'll see I'm back at address 15. So now I'd like to go and make sure that I have my contents of the memory entered correctly. So I'm actually going to step back an extra step just to make sure. So I'm going to go back to 013. So I'm going to clear the input buffer, 0, 1, and 3. And I'm going to set that as the address. And then I'm going to do memory read. And we should see 1. Memory read should see 331. So our corrected byte has now been made. And then I can go ahead and see the next one, which is 321, which is as expected. So now I'm going to go ahead and continue checking the rest of the program, and we'll resume when I've done that. Okay, so we're done. So this program has now been entered into our device here. So what I'm going to do here is we can now start our program and see what happens. So we do that by simply pressing the start button. We've already set the program counter as part of the memory here. So there's no need to set it separately if you're familiar with other machine code programming devices. We can just go ahead and press start. And at this point, the Kenbak shows a couple of LEDs lit on the screen. And as I mentioned, the purpose of this program is to provide some kind of game or test for us to convert from binary to decimal. In this case, we can see 5 is represented here. 4 plus 1 is 5. And so what it wants us to do is it wants us to illuminate the 5 LED here, the LED in bit position 5, by pressing the light or the button to illuminate that 5 LED. Then I go ahead and press the start button and it will go ahead and check our input. Now, because we got that right, it's actually gone ahead and give us the next test to complete. In this case, it's 2 plus 1, which is 3. But maybe I don't know my binary that well, and I think that's actually a 5 as well. So I press 5 again and press start. And you can see, because we got this incorrect, I now have to retry that test until I get it right. So if we go ahead and acknowledge that that is indeed a 3 and press start, we'll see now we have no lights illuminated, and that's a perfectly valid bit pattern. In this case, of course, this represents 0, but I need to illuminate the 0th position LED. If I just press start here, it's going to keep telling me I'm wrong. I need to illuminate that 0th position LED, press that here and press start, and then it will give me the next pattern to check, which in this case is 4 plus 2 or 6. And then just the 4 LED is illuminated, the one valuing 4 anyway. And we press 4 to continue, and then so forth. So let's think a little bit about how this program works. So I've got some comments in the right-hand column here of my worksheet, and we can go and look at those as we go through. So when we entered the data, we ended up clearing the various registers that are available. So we're entering the constant 0 into register A, B, and X, and A, B, and X, these special locations. And we set the start location, as I've already mentioned, to the start label here. We then have 2 lines of code, which we're going to skip over now, because if we were trying to run the program, that's exactly what the computer would do. It would skip from the program counter. It will start at the program counter location and start executing from this position here. So what we're going to do is we can look at start, and we can see the first instruction here adds to the register B, so that B location, it adds a constant, and in this case that constant is 055. The comment here is that this is advancing us to the next test, so it sets the B location to contain the test value, and it's adding 055 to that location, which is obviously outside the range we were seeing here, so we'll maybe see a little bit how that was working in a few lines' time. The next few lines prepare the test value, and that's what's going to happen interestingly here. So I'm actually going to go ahead and before we start that, I'm going to clear the input buffer just so I can represent this 55 visually, so we can talk about how that works. So that's 055, as that looks like this. And these next lines here, they load the A register with the constant 070. And if I go ahead and set that up on the display here, you can see that's 070. Now, underneath here, in the next few lines, we AND the A register with the B register. So in the A register, we have this 7 pattern, and in the B register, we have that 050 pattern. And when we AND them together, that checks to see which LEDs are illuminated in both patterns. Now you can see here by me flipping between those two, the only 2 LEDs I don't have to switch that are available in both of those patterns are the LEDs indicated by the 5 and the 3 here, these 2 LEDs here. And so when we AND those together, only these 2 bits are preserved and they're stored back in the A register. The next 2 lines go ahead and do a rotation of the A register, firstly by 3 places and then by 2. In this case, it rotates left, which means moving the bit pattern to the left. And to do that, what it does is it looks on the left-hand bit here, this 7 bit, and it copies it into position 0. And position 0 gets copied into 1, position 1 gets copied into 2, 3 into 4, and so forth. Now to do that, it actually has to preserve the value of 7 kind of in a spare memory location just temporarily, otherwise it accidentally overwrite everything. So we can just think this is a 0, and we'll just remember that very carefully. And then we'll just simply copy the value from the right-hand side to the left-hand side. In this case, 6 to 7, so we're copying a 0 into there, that's all good. 5 into 6, well, that needs to illuminate 6 now. And 4 needs to copy into 5, well, that needs to be extinguished. 3 into 4, well, that needs to be illuminated. 2 into 3, that needs to be extinguished. 1 into 2, well, that stays the same. 0 into 1, well, that stays the same. And then that spare value, remember, that 0 value goes into here, and that stays off as well. And so that's done a rotation left 1 time. Now, this instruction actually does that 3 times. And then immediately afterwards, it does it another 2 times. And the overall effect of that is to move the bit pattern to the right-hand side of the display here. In an 8-bit device like this one, you might also consider that to be a rotate right 3, that is moving the data 3 bit places to the right. The final thing it does here, before we move on, is it goes ahead and stores the A value, this pattern we now have in the A buffer, into a special location 200, which is actually the output buffer. Now the memory location 200, when the program is running, is mapped to the LEDs here. It's copied into the LEDs, and so that means that this whatever pattern here that we copy into the 200 location ends up on the LEDs, and that makes a lot of sense, right? So when we first started running our program, we did indeed get a bit pattern of this, which represents 5, on the display. Next, we go ahead and we are choosing to store the value of X into the input buffer. So I mentioned that 377 is this special input buffer. And what it does is it's copying the value of X, which is all zeros, into the input buffer. And the purpose of this is simply just to clear the input buffer. And that means that when the user goes to enter something in the input buffer, the value is as expected. It's clear until they choose to illuminate a particular LED. The program then actually goes ahead and stops entirely, and it essentially lets the user switch back to input mode so they can store something in that input buffer before resuming the program. And so the user will enter something into that input buffer of their choosing, and then they press start, which resumes the program from where we have just finished. And that next instruction goes ahead and it rotates left the A buffer by 3 places. Now we've already done that once before, and so if we move everything over 3 places, we can see that we end up with that bit pattern here with the value here back in the middle that we had earlier. This begins the configuration for the check, and what it then goes ahead and does is it adds the value 202. Now that's easy to do here because we can just turn on, make sure we have 2 in this position, we don't add anything to this second position, and we add 2 to this position. Now this is kind of interesting in that then the computer goes ahead and stores that particular bit pattern into the location check up here, okay? And so it copies this bit pattern into this check location. So it was 000, but now it's going to contain this value 252. And then it goes ahead and it jumps unconditionally to the check location. Now, what does this really mean? So what we've done here is we've created our own instruction dynamically. The computer has created the instruction dynamically and copied it into memory here. So this is quite a clever and advanced programming technique in that they're actually constructing an instruction on the fly. But what does the instruction 252 do? Well, we can go ahead and we can refer to our summary of instruction coding sheet. And what we need to do is we need to find something where there's a 2 in the rightmost column here, and a 2 in the first column here, 2. And this says skip on 0 if the digit position, whatever's in the middle here, is a 0. So it skips if whatever is in this digit position is a 0. Now this is actually a 2-byte instruction, and so which particular memory location is it going to test? Well, we can go ahead and look at what is the instruction after check, or the contents of memory after check. It's the input buffer, right? And so this is going to skip on 0 if the input buffer in the position of that middle digit is currently 0. Now, that middle digit we've asked to be 5 in this instance because we have that 5-bit pattern in the middle. And that means it's checking to see if the 5th LED has been illuminated and been set by the user in the input buffer. If it hasn't been set, it skips the next 2 bytes of memory. Now that can be 1 or 2 instructions depending on the instructions, but it always skips 2 bytes of memory. It goes forward 2 positions. And so the result of that is that if that particular bit pattern has not been illuminated, that particular location has not been illuminated by the user in the input buffer, it's going to skip this 2 lines of code, which advances to the next test. So it won't update the pattern that we're asking the user to check, and it leaves the same pattern and it goes through the same code, which moves it on to the display again. So I think this is a really clever piece of code here that means that we can skip it and present the same test to the user if they've made a mistake. But if they haven't made a mistake, if they have indeed illuminated that pattern, then it goes ahead and it advances to the next test by simply adding 55 to whatever memory location is it, or sorry, any data that's in memory location B. And so that'll advance to the next test. And this gives us a sort of pseudo-random series of numbers to test. So What's interesting about that is if we think carefully now, all this checking instruction is doing is just checking if that digit, that particular LED has been illuminated. And if it has, then it says that you've got it right and it advances to the next test. Now, if we clear this display for a second here and we resume our program, we can see we're currently in a game here where we're expected to press the 1 LED, because this is illuminating the 1-bit position of this binary value here. And so to pass this test, we would have to illuminate the 1-bit position here. But we can cheat actually by simply illuminating all LEDs and pressing start, and it'll advance to the next pattern. And the reason that works is because it's checking to see if that value, 1 in this case, has been illuminated. It doesn't check to see if any of the other ones are incorrectly illuminated, it only checks that particular value. So in this case, this is 7. 4 plus 2 plus 1 is 7. So I could go ahead and illuminate everything but the 7, and it will say I'm wrong. But I could illuminate 7 and any other combination that I like and start, and it will decide that I'm actually correct. Now, obviously, that's not a great way of playing the game. It's not going to help you learn your decimal to binary, binary to decimal conversions. But that does show a limitation of this particular mechanism. But it's a very clever coding technique where we're dynamically generating the instructions on the fly. Now, there's one more thing about this program that I thought was kind of interesting. As I mentioned, at this particular position here, we do a rotation to the left 3 times and then rotate to the left another 2 times. Well, if we actually check the instruction coding sheet here, we can see there actually is a right rotate option available. So we could choose instead to rotate 3 positions to the right, which would have the exact same effect. And we can choose to rotate right the A register by 3 places. So to rotate right, that would be 1, 3, and the last digit has to be a 1. So it's 1, 3, 1. Now that would mean that rather than using the 2 instructions that we have here right now, we only need 1 instruction. And that could potentially shorten our program. So I've gone ahead and I've made a little addendum to this program here as follows. And so now we can rotate right A3 places. And what I've done here is I've inserted a no operation or a no-op or a noop into memory location 15. Now the reason I need to do this is because otherwise I need to go ahead and change the mappings of all of these things here. For example, I'd need to move all of these instructions up 1 to fill up this space. But I could do that, and that would be an interesting approach that we could use. So I can go ahead here and actually can go ahead and change those 2 instructions, doing a correction to our program. And so I can clear the input buffer. I can now set the address to 014, and set the address. And in here now, I can enter the value 131, 131, and I can store that in memory. And that will advance us to the next location, 15. So we have 1 and 5. And in here, I can put the no-op instruction, the 200 in this case. So I'm going to clear and put in 200 and store that as well. And if I then clear this display and press start to run, you see we now still have the same bit pattern we had a moment ago, which is our 5. And if I enter anything else other than 5 and press start, I get the same bit pattern. If I choose 5 and start, it will give me a new bit pattern, and I can still cheat the same way by filling in everything here, and this will advance us in this case to 0, and I can get that one right as well and give us another bit pattern. Now, actually for the no-op instruction here, there's an interesting fact that for no-ops, we can have either a 2 or a 3, any value, and it must end in a 0. And so I chose to use 200 here, because this minimizes the number of buttons I have to press, right? And actually, you can see in this program, there are some cases where you might do that to try and minimize the number of inputs the user has to do, number of toggling they have to do, especially important for the beginning of the program. So one thing here, we're doing a rotate right here, and I'm doing that to preserve the original coding intent of it, which was to, as we noted previously, to rotate left 3 and 2, which I say is the equivalent of rotate right 3. But actually, there is a slightly shorter instruction, a few less bits we might have to apply. And in fact, we could have instead gone with a shift to the right instead, which actually doesn't require us to illuminate that first bit at all. Now that works because when you shift to the right, it does what's called a bit extension. Anything that's in the leftmost column, the column 7, gets copied across, and it doesn't do the looping pattern we saw before. So it's actually slightly more efficient. There's less to store. So we can use that. We could have used that instruction instead. And so we could have done this right shift, and that would result in the program code 0, register A, plus 3 places. So 0, 3, and then 1 is compulsory. And so again, I have another addendum to the program which does that instead here. And so now we can instead shift right by 3 positions, and we still need a no op instruction underneath as well. But again, I can go ahead and I can clear my display here. I can set the memory location to 014 and set the memory address. And then I can clear this, and instead of having 131 in there now, we can have 031, 031, which is a few less lights to illuminate. And then we can store that in memory. And in 015, we can see, to make sure we've advanced, we are indeed in 015, and we can read that location as well. And we can see we still have 200 in there, which is perfectly fine. So if I clear now and I press start again, you can see we have a bit pattern of 5 that we are expected to represent. And of course, I can go ahead and press 4, for example, and it will tell me I'm wrong. I can press 5, and it will tell me I'm correct, and move on to the next pattern that I need to decode. So as I say, I could have gone ahead and moved all of these instructions up, correcting any address references as necessary. In this case, I don't think there are any that would need to be corrected, but it would require me entering a lot more code into the device to correct for that shift. So I can leave that as an exercise to the viewer. If you want to go ahead and do that, of course, do feel free to do so. Maybe there's other optimizations in this program or any of the other example programs from the Kenbak exercise book, and I'd be really excited if you'd share those with me. I'm going to provide a link both to the Adwater Stir website, where you can pick up this really nice Nano Kenbak-1. It's only $25 currently, which is really great value, I think. And I'll also link to a web-based emulator as well if you'd like to try any of these exercises out without heading over and buying a device at the present time. Okay, so I hope you found this video about one of the earliest personal computers really interesting, and I hope to see you in the next video.